Okay, so
yeah. Thank you very much. Thanks for having me here. Today I'm going to present our work titled with Building Up Quantum Spacetimes with BCFT Tensor Networks and Symmetric Quantum RG. So this talk is basically mostly building up on these works, and this work I'll mention because it's related to our upcoming work related to the RG formula, so I included here, and some work in progress. So the question we want to ask is the following question. So since the discovery of the ADS-CFT correspondence, we actually have understood a lot about ADS quantum gravity using the duality. But there is a question that remains, I think, unsolved. So actually, is there a way to directly or even locally see that geometry or gravity emerges from the algebra or in the CFT, especially the algebra today, I will be focusing on the OPE algebra instead of the von Neumann algebra people talk about these days. So the question actually falls into the category of the program called bulk reconstruction. And especially the question I want to ask is there a way actually to reconstruct the bulk geometry itself instead of usually what people consider this problem, they construct operators on top of a fixed background. And if this can be done, the question is, actually, can we see that the bulk direction is somehow related to RG flow that actually originates from the very beginning of the ADS-CFT correspondence? So one idea along this line actually comes from the analogy when people compute the entanglement entropy for the boundary system, which is the famous Ryu-Takayanagi formula, which actually look a lot like when people compute entanglement entropy in tensor network representations of condensed matter systems. So just let me be really brief. A boundary is given on this circle, and I compute the reduced density matrix. I bipartite the system into A and N complement. I trace over half of it. I get a reduced density matrix. The von Neumann entropy is called entanglement entropy. And in that's good. Okay, good. Thank you. So in holographic systems, it had been observed that this quantity is given by minimal surface. The area of minimal surface in the bulk that's homologous to this boundary subregion divided by 4G. This formula look a lot like the entropy formula, and it actually look a lot like what people get when they study tensor network representations of ground states in condensed matter systems. And since then, efforts have been people have tried a lot of different things, cook up with a lot of different models trying to represent some properties of holography in terms of these tensor networks. I'm showing you some of the very famous ones and including one of the most recent one. They are all great. They capture some aspects of the holographic dictionary. However, there are some, I think up to this stage, it's fair to say that it does capture many aspects of the holography. However, there are two things that are missing. First of all, where is the CFT? Secondly, where is gravity? So these are all toy models that actually, most of the toy models up to now doesn't have either of the ingredients. They capture some aspects, but these two are still missing. And we definitely want to go beyond toy models to find something that can really represent both, to see actually how these two ingredients are fit into, if this program really makes sense instead of just toy models. And today I want to tell you it is actually possible. So I will show you actually a brand new step-by-step procedure in CFT2 that you can use to derive an exact CFT2 tensor network. And from that, there is an emergent ADS3 spacetime tensor network out of it, using what I call BCFT Legos. So I'll explain it, what it means. So the crucial idea is really the tensor network is coming from really discretizing the CFT passing the group, which can be done exactly actually. So the ingredient is you use the BCFT 3-point functions and something we invent called shrinkable boundary. Then once you combine these two, it exactly discretizes this CFT passing the group, realizing a continuous field theory on a discrete lattice. So this gives you an exact tensor network representation for 2D field theories. And then we can see actually from this construction, there is a very natural way to see that actually a non-perturbative 3D bulk will pop out if you stare at it carefully enough. They are hiding in the structure constants actually in this construction. And this actually gives you an exact holographic tensor network now for the 3D theory instead of 2D theory. And what the role of the 3D bulk emerging from this construction is it makes the 2D generalized global symmetries manifest. This is a very rapidly growing subject, which Clay is a very pioneer of it. So we are making use of many of the aspects of the recent understanding of these aspects. And we will see that actually from this perspective, there's really an RG flow in 2D. And you can see a symmetry-preserving RG, which I call symmetric quantum RG, is actually can be shown to be, in a rigorous sense, to be related to radial evolution in 3D bulk. And these are very generic. I haven't tell you where is gravity. Really, in 2D, when you see that when the bulk preserving certain Virasoro topological defect lines, the bulk you will get is something called Virasoro TQFT squared. And that was recently proposed to be the exact quantization of 3D gravity. And you can see immediately a large C limit give you the Einstein-Hilbert action, which is gravity. Finally, I will come back to the original proposal. These are all for the whole space-time, the path integral. And we will show actually how this construction, when applied to wave functions, which is the original proposal, can be used to derive the Ryu-Takayanagi formula.
Is this way of discretizing 2D CFTs similar to what Brehm and Runkel do, where they cut a hole? And
exactly. Yes.
It's the same?
Yes, it's actually quite interesting. Let me see how to say this. The boundary condition, at that point, they didn't know, but it's exactly what Janet and Gabriel found like 2 years ago independently before that paper, but it's exactly the same actually. Yeah. Let me just mention one more thing, because in the talk I will go back and forth between 2D and 3D, so I use different colors. So most of the time, the blue color representing the boundary stuff, and the red color representing the bulk stuff. So just to explain now. So okay, let's just begin. So the outline of my talk is, I will first tell you there are 4 steps to construct a spacetime tensor network. So the step 1 is really to cut 2D CFT path integral into pieces to discretize it. And we'll see actually how to do it rigorously and give you a 2D exact tensor network. Then once we are done with it, we will see that there is a natural way of rewriting it. And when you rewrite it, you will see part of it will give you a 3D bulk interpretation that may turn it into a 3D tensor network. These are for a single layer of the construction, and we definitely want to see RG. So when you see RG, actually, I want to see how to construct more and more layers. That was the initial actually observation by Swingo relating MERA to tensor network. And we will see actually in this construction, there is a natural way already hidden in the construction where you can build a real space RG flow. And the Callan-Simonsen equation will be related to the Wheeler-DeWitt equation in the bulk and related to the TD bar deformation that people studied recently. Then I will show you actually how to see gravity using 2 examples, one of which is the Louisville CFT, which itself is not a conventional holographic CFT, but it does capture many of the features. It has gravity in it, and I will tell you the difference. Then another example is you can do the ensemble average, and you will also see gravity in the bulk. Then we will come back to how to apply it really to wave functions. And I will show you the simplest example where you can derive the RT formula and see where the rule, like for example, in perfect tensors, the heavy code, actually is encoded in this construction. In the end, I will come back to generalized symmetries and see actually what is the relationship between holography and the recently proposed SIMTFT, and see its implications for the factorization puzzle. And that's the plan of the talk. Let me just begin. The first step is really to cut 2D path integral into pieces to discretize it. So in 2D CFT, we're used to compute partition functions or correlation functions. In this talk, I will mostly focus on correlation functions, but everything can be, the partition functions, but everything can be generalized. We can talk about it in the end. Using the so-called closed pair of pairs decomposition. So for example, I'm using this genus 2 partition function as an example. You cut it into the so-called pair of pairs, closed pair of pairs. So there are 3 boundaries, where each boundary is a circle. Then I glue them together. In CFT, the gluing in path integral is given by summing over intermediate states. In CFT, the complete basis of states are labeled by primaries and descendants. You sum over all of them, and then you reproduce original path integral. This is the way we usually conventionally do the CFT computation. And first, I want to introduce another way of doing this, which is to cut this into pieces. Yeah, by the way, I should include this reference here as well. It's also what Runkel and Brehm did exactly. So there is actually another way of doing this computation, which is to, instead of doing this slightly, there is a more local way of doing it. Instead of cutting it into closed pair of pens, I cut it into triangles. Let me just first start by using the example of rational CFTs because I don't want to deal with divergences now, but we will deal with it later when it's more related to gravity. So really, so the first step is suppose let's still look at this genus two partition function. I cut my 2D manifold into chipped triangles. So I triangulate it. So why are these red dots here? Because I still want to insert a complete spaces of states, just as the previous example, but now the states are living on intervals instead of circles. For intervals, I need boundary conditions. So just to exaggerate a little bit, I put these red dots here. And there are also divergences related to that. So let's first keep the whole size finite. And I will show you how to actually regularize and get rid of it, represented by this. So if I choose boundary conditions, on each of the point, I choose the so-called conformal boundary condition. Then on each of these lines, there are two conformal boundaries. I label them by sigma. And the intermediate states are labeled by the primary label and descendant labels. And using the state operator correspondence, each of the state here can be represented by an operator. It's called boundary condition changing operator. I might just call it boundary operator later. It has three labels. I'm suppressing the descendants because they are fixed by conformal symmetry. The primary labels have a primary index alpha here and two boundary conditions labeled by sigmas.
Sorry, just to make sure I understand the picture. So are the red sites in the picture where you are going to open holes, or are the red sites are where the holes are?
Yes.
Are you also supposed to sum over all possible conformal boundaries?
I will explain it. Yes, and the sum is very crucial, and you cannot sum them arbitrarily. They're the preferred weighted sum to do. Yes, very good point. We will come back to that.
And the goal is that after the proper summation, you are going to recover this partition function.
Exactly. So each of the triangle here, now it actually, you just do a conformal transformation or do it larger. These are the so-called open pair of pens because there are three states here and three boundary conditions. And the state operator correspondence means that you can conformally map these contributions to the upper half plane where you insert three operators on the real line. So, and the conformal map is explicitly known. You can use the conformal map, you pull it back, then you get the contribution on these triangles. And the claim is that actually to construct a CFT tensor network, these will be my tensors. The contribution now really depends on 9 labels. 3 of them primaries, 3 of them are descendants, and 3 of them are boundary conditions. The tensors have 9 labels. Actually, it depends more, for example, on the background metric, on the shape, on this radius of the hole I cut out. So I will just put all of them here. And the interesting thing is that due to conformal symmetry, actually the answer factorized into 2 parts. The first part only depends on the boundary condition and the primary labels. These are the so-called BCFT OPE coefficients. If you're familiar with the closed story, this is analog of that, but now it depends on boundary conditions. And all the position-dependent pieces, they will factor out into another piece where all the descendants actually are, the dependents are here, and they do not depend on the boundary conditions. These will combine into the conformal blocks. So it factorizes into these 2 pieces, which actually will be important later. But let's just first move on. So indeed, very good point. First, let me fix those boundary conditions before I do the sum. So when I fix them, the rule of gluing path integrals will tell you on each of the lines, I sum over the complete basis of states, which are labeled by primaries and descendants. So I sum over them. And the total path integral will now depend on the choice of boundary conditions. And also the whole is still here, so I put the R here. And just notice that from this expression, it's clear that the sum over descendants gives you the usual definition of a conformal block because it is just what it is. And the interesting thing is that now the holes are left open here and they are labeled by boundary conditions I choose to put on these holes. So each of them have a label A here. So it finally depends on all of these labels here, A. And the goal really is to get rid of these holes. So to reproduce the original CFT path integral. So how to do that? I say I close the hole, really I want vacuum in the tiny hole. If it's vacuum, then you are doing nothing to your path integral. And the proposal is really now instead of fixing the boundary condition, I do sum over boundary conditions. And we call this shrinkable boundary in the original Janet and Gabriel paper. Ronco and Brown call it what's the word? Cloaking boundary condition, yes. And I'll just explain here why that's the case, why that's the name. So the idea is really we do a weighted sum over boundary conditions with a very specially carefully chosen weight. For experts, it's the quantum dimension associated to these boundary conditions. If you don't know what it is just a number, and I will tell you why you pick this number now. So the idea is really there are two ways you can see why it's good to choose this boundary condition. First, choose this weighted sum, choose this weight in the weighted sum. First of all, using the open-closed duality, instead of viewing these as boundary conditions, now I can do radial quantization. I view these as states living on these circles. So if I view the quantization in this channel, these states will be something called, for a conformal boundary condition, they will give you the so-called conformal Cardi states, studied with Cardi. And if I do this weighted sum, the weighted sum will turn this Cardi state into the so-called vacuum Ishibashi state. Vacuum Ishibashi state is just a vacuum state plus a lot of descendants, left and right paired together. And you will see, interestingly, for example, this state is very special because all the descendants are made up of the stress tensors, and the leading correction is, for example, in this sum is the -2 descendant. So it is actually the TT-bar operator if you write it in the operator formalism. And
this Ishibashi state is not a legit boundary condition. It does not satisfy. So why is it legal to have that as a boundary?
For each fixed alpha, it is a boundary. So I do a weighted sum. You probably not call it boundary condition because it's a sum over boundary condition.
But I mean, more generally, why do you actually need to hit the vacuum Ishibashi state? Why wouldn't any boundary condition that has a vacuum contribution would be enough, and you just tune to suppress the other contributions?
Good question. Yeah. Let me tell you the reason. Because if you only have finitely many of the holes, you're right. You can just shrink it, and the vacuum will always dominate. But if suppose you dig more and more holes, you will see that it doesn't flow back to it's like. If you dig more and more holes, the subleading operator will try to deform your theory.
Right, but you would have to tune it, right? I mean, that would be like a standard lattice model where you have to tune to hit the critical point.
Good point, yes. And the claim is if you do this weighted sum, it's already at a fixed point. You don't have to tune.
So this is like the tuning somehow?
Yes. It's related to this comment here, actually. Because I'm going to tell you the quick answer is this sum, actually, that was the motivation by Brown and Ronco.
Yeah.
It preserved the topological symmetry, so it preserved criticality. And also, it's kind of cheating, but when you do this weighted sum, you see this really bulk. From the CFT perspective, actually you're right, and you don't have to do weighted sum. Anyway.
I guess the thing I'm just trying to make sense of is that the Cardi condition usually comes, but when we say that we want the interval Hilbert space to have, be an honest Hilbert space with integer dimensions.
Yes.
Are we using that condition? We're not using that condition anywhere here? I thought we kind of are.
For each fixed sigma it is. But if you do the weighted sum, it's not. And should I continue actually? Yeah. This is the TT-bar operator, which is not surprising. Later we'll see it is related to the connection people propose relating to TT-bar and other stuff. More importantly, as all the descendants are made up of the stress tensor, the topological defects in this series will all be preserved. What does that mean? So nowadays, the current understanding of generalized symmetries is that symmetries are labeled by topological defects. When you do this weighted sum, you can consider inserting a topological defect in the theory. When you do the weighted sum, the boundary conditions are that they can move freely across these defects as if they are not there. So you can do the computation and see that anywhere you insert it is the same. It's telling you that the topological symmetry is preserved. You can also see this by noticing these are all made up of stress tensor. And it was already observed in the condensed matter community that when you preserve all the topological symmetries, it's actually the relevant operators, it's very easy to kill all of them. So all of the operators left will be irrelevant. And that's the reason why we can find an exact answer. You don't have to do any tuning. It's already at the fixed point when you shrink the whole set to 0. So this means that the holes actually can be closed. It is the, when you do this, when you take the whole size to 0, there's a universal Casimir energy contribution. When you multiply it, it reproduces the original CFT answer. And this is the proposed fixed point tensor network, actually. And yeah, maybe let me just move on to the 3D part, which actually, yeah.
One probably technical question. So this requirement, so the sum is over all Cardi states?
Yes.
And this requirement that your combination gives you just the vacuum Ishibashi uniquely fixes omega i's?
Yes, for irrational safety. So now let's see where 3D pop out. I think it's pretty cool. So I already told you that, let me first fix finite R. So this is the expression. Now let's try to rewrite it, actually. When you rewrite it, I would also do something actually kind of natural. Now I will rewrite it as an overlap of two 3D quantum states. 3D quantum states are defined on the 2D surface, which is the surface initially I do the triangulation. And I'll introduce an Hilbert space that's actually where the states are defined on these lines. And on each of the line, I gave it a label, which is the primary. And we'll see, very interestingly, this is the Hilbert space of a known theory, actually. It was the theory discovered by Professor Levin here, the Levin-Wien model, actually. So these states are defined as on the line. And what I would do is I would collect all OP coefficients together. I find the first state. I collect all the OP coefficients together with this weight. I define a state. And the other stuff, I would just collect them into another state. So you will see that in this guy, it actually, each of them are conformal blocks because I sum over descendants. And for this one, it doesn't depend on the descendants. And what is that? I'll just explain it in the next slide. But first, let me make one comment. This construction already exists in literature. It's called a Strange correlator. And when people in the condensed matter literature, people notice that for many of the lattice integrable model, including the Ising model, actually, you can write it as an overlap between two quantum states. One state is exactly this state. For example, for the Ising model, you use just rewrite it, you will see this one. And in that case, the omega, I choose another omega, which is a direct product state. And you will see this reproduces a lot of the lattice integrable models. And it was already proposed that maybe I can do RG flow to a critical point such that this guy will be the fixed point. And this actually is exactly realizing the idea.
So here you separated it into kinematic part and dynamical.
Yes, exactly. Exactly. Yes. Yes.
What do you have to do in terms of like the manifold which bounds your two manifold? Like,
Who is with what of the manifold?
Like you said there's an emergent 3D bulk, like
not yet. I will show you.
Okay.
In the next slide. There is a magic here, actually. Very interesting. The BCFT OPE coefficients, they were actually realized initially by Ronco and then later generalized by Fuchs, Ronco, and Schwiger. They are proportional to the so-called quantum 6J symbols of some quantum group. These quantum 6J symbols, actually, they come exactly from a 3D path integral of a TQFT. And the idea is in this TQFT, it's a discrete TQFT that's called the Ryu model or equivalently the Levin-Wien model. So in these TQFTs, this quantity here can be obtained by doing a path integral on a tetrahedron with a boundary. Especially 3 of the boundaries, you can choose them to be primaries. 3 of the boundaries, you can choose them to correspond to the boundary conditions. And in the original picture, what will happen is the edges are still living on the 2D boundary, and you shoot some rays into the third direction coming from these corners, actually, and they meet in the bulk somewhere. And the interesting thing is that the weight we choose here is exactly the weight in this TQFT to make sure that the stuff you get in the 3D TQFT is triangulation independent. For experts, this is coming from the pentagon identity of these 6J symbols. So when you write this, you see this state is nothing but the quantum states coming from, you insert a boundary. So original manifold living on this, imagine you have a solid ball. On the boundary, you have a ball. You put the 2D CFT there, and you have 2D manifold on the boundary. You just triangulate it, then shoot rays from the corners into the third direction. Then meet in the center, and then you have a lot of tetrahedron, which is cut by this boundary in the bulk. You do the path integral of the so-called Ryu or Levy-1 model with a boundary condition chosen by the 2D boundary condition, actually. And the path integral exactly give you this quantum state. So this, you will see, it's actually kind of cool that when we do this weighted sum, it's exactly related to the fact that you preserve the topological symmetry. I will mention this in a couple of slides. So you will see, actually, this, the 3D emerges from the BCFT OPE coefficients with this weighted sum. And what about the other one? The other one is just giving you another quantum state that's coming from these conformal blocks. It does capture all the position dependence, the length, the scale in the problem. Actually, it is something called a PEPS state. But the important thing is that I think people in condensed matter literature are also interested in this because this will be a fixed point tensor network with infinite bound dimension, realizing a fixed point of a CFT. So when you combine these two together, actually you map the 3D TQFT to the 2D CFT. So why does it work? It will look like magic. There's a better reason of it. It's really related to generalized symmetries. The reason is because, so now I draw a projection of the previous diagram. The bulk theory, previously it's made up of tetrahedron, now made up of triangles. So you do this path integral on this shaded yellow region, I get a quantum state on this red edge. Now the claim is that for a theory with one lower dimension, you can find one boundary condition, which is labeled by this blue edge. When you contract the indices here, which means you take the overlap, it reproduces the original theory. So if you have followed the developments in general symmetries, this is exactly the so-called sandwich construction, where the bulk theory, together with the orange stuff in the middle, which is called topological boundary, is what people call the quiche. In this case, it captures all the dynamics because it captures the OPE coefficients. And the other one is the blue one, which is the conformal block, is the so-called physical boundary condition. It captures everything that's non-topological and scale dependent in the CFT. So people draw this diagram, why it's called sandwich, because the claim is you can suppose you have lower dimension theory, you can pull it open by using its symmetries. You promote the global symmetries to get gauge symmetry, then you find two boundary conditions such that the higher dimensional theory can be collapsed to the original theory. And I'm including a lot of the references here, including a nice review by Clay. So if you're interested, you can read them. I'll come back to that because there are more stuff related to the tensor network I want to say. But if this picture is really how holography emerges, then actually it automatically solves the factorization problem. I will come back to that. So now we have introduced a single layer of 3D bulk. It looks like this. It's kind of boring. You might say you are just doing simple rewriting, so how to make of it. And we know that when we think of tensor networks as useful, we really want to have multiple layers of it. If you have heard of it, you want to see the MERA type structure of it. So, and that's related to RG flow. So where is it? Now I'm showing you actually you do have it. So let me first make this proposal. I will explain it a little bit more. The proposal is really, ADS-CFT, it actually has been proposed from the very early days. It's relating the partition function to the radial Wheeler-DeWitt wave function in ADS. And that's actually what our formula is doing, right? You have a state that's specified by quantum gravity, and I find a basis of state, which I write as omega. So this partition function is just a wave function. And I have told you psi is a very special state. It is a ground state of a TQFT. Now I want to show you actually omega is also very special. And really the information of the RG flow is encoded in omega through the interplay with psi. So what's the idea? The idea is really that psi as a TQFT ground state described by a lattice system. Actually, you can have different descriptions using different lattice scales. It's covariant with respect to the triangulation. So these lattice scales for TQFT doesn't mean anything, but it's just a reference you choose. So how do you think of this lambda? It means the length you choose on these edges. And as a TQFT ground state, I can choose to triangulate the boundary as I want. So for example, I can use these blue edges to triangulate it. It has shorter length. You can also use the one that's a little bit inside, where you use the green edge. The green edge is longer. So the next slide, using 2D picture is easier to draw, but I just want to give you some impression. But these two are actually related because this is a TQFT ground state. You know exactly how this is related to that. For experts, this is related to the pentagon-to-pentagon identity again, or it actually is directly translated to the BCFT crossing relation, which roughly speaking just turns 4 triangles into 2. And we will call this, this operator relating the 2 triangulations as U. Let me just show you an easier way to understand it. So really, when I do the projection, the state is defined to be on these red edges, which is built up from my BCFT OPE coefficients. Now I have a state defined on these red edges. These red edges are short. I want to know if there is a way to relate this state to a longer green edge. So how do you do that? The bulk is a TQFT. So instead of doing this triangulation, I can change my triangulation like this. In 3D, that's the 2-3 move, but in this case, it's 2-2, so it's simple. Now you can see in this diagram, the stuff below actually has a longer edge instead of a shorter one. And to relate these 2 quantum states, you exactly glue this triangle on the top to it. So you know that to relate something that has in TQFT with a shorter scale and a longer scale, I just include this triangle contribution to it. And not surprisingly, this triangle contribution is the path integral of the 3D TQFT. I will call this stuff U, an operator U. And the idea is really that now this quantum state needs to be contracted with the blue edge, which give my omega. Now, instead of gluing it to the psi state, I glue it to my omega state. Psi state is a TQFT ground state, so it doesn't flow. But when you contract it with the omega state, actually it starts flowing. And the interesting thing is that by construction, this is a real space RG transform. You change 2 shorter lengths to a longer length. And this actually was initially how this was discovered by Janet anyways. And moreover, this is actually exactly the real space block spin transformation that was initially discovered by Kadanov here. And more important, what we actually input into this construction is that these ones coming from the bulk sim TFT path integral actually preserve the symmetry. So actually give you a symmetry preserving block spin transform. And you will see omega state now start flowing. Really the idea is that the state I wrote when you take R goes to 0 is a fixed point of this RG flow. So this is just one layer. You can just imagine now I include more and more layers. So it will be interesting because now suppose I do a very fine triangulation. I glue more and more triangles into it. In the 3D picture, it's gluing tetrahedron onto it. You go deeper and deeper into the bulk. And that's actually exactly the essence of the MERA tensor network. And we are seeing it does exactly have this structure. And different series, they preserve the same symmetry. So how do I see that they are like, how do I see different series on RG trajectory? You will see actually they are exactly given by different omegas when you combine it with the triangle. Let me skip the technical stuff here. And you can have different physical boundaries, different omegas. You can contract it with psi, you get different series lying on the same RG trajectory. And importantly, different slices or different theories are exactly related by gluing 3D bulk path integral onto it. This is not the first time you see this, because if you have studied TT bar deformation, that's also exactly how it works. You glue the 3D path integral onto the 2D theory and relate them together. It's beyond an analogy actually. When you are close to a fixed point, really you can see that the size of the hole, because I just told you the subleading correction is the TT bar operator, it actually at leading order is doing the TT bar deformation. And on this lattice, at higher orders, they will be different, but it's non-perturbably defined. And you can study the Kalan-Semantic equation of it. You will see after some manipulation, this exactly translates into the Wheeler-DeWitt equation in the bulk. Actually, it's physically very reasonable because what this equation is saying is nothing but the fact that the Hamiltonian of the PQFT actually annihilates my state psi. So this is a ground state. So the ground state condition is the Wheeler-DeWitt equation. We actually is also sort of know in gravity. So why do I call this quantum RG? Because it was already observed by initially by Polchinski and in this paper, and also by Sonsik, that usually in RG the couplings are classic; they don't have dynamics. But really, in order to include dynamics, you should because single trace operators will generate double trace operators. So the idea is really to project the double trace back to expand it in single trace again. When you keep doing that, it generates dynamics. Here, we are seeing similar thing, but really we are projecting not onto single trace operators, but we are projecting onto simple operators. So each of the RG step I project onto simple operators that actually make the source of the metric, which is the metric field in the bulk dynamical. And here we are seeing this actually coming from a symmetry consideration instead of the single trace, double trace, large n consideration. So what I told you is, or generic, it works for any 2D CFT. So where's gravity? So let me just show you. Looks a lot like gravity, but really where is gravity? Let me just show you 2 examples. It really works. The first example is Liouville theory. Let me just emphasize again, it's not conventional ADS3 quantum gravity because the measure in this theory, the geometry you sum is not the conventional sum we want to sum, especially like the vacuum. But anyway, we can study it. It does have a gravity dual, which I'll explain. So this is an irrational CFT. Now, for irrational CFT, the spectrum is, in this case, it's even continuous. It's labeled by still labeled by primaries and boundary conditions. Fortunately, there are preferred boundary conditions called FZZT boundary conditions. And in those cases, all the structural coefficients for the BCFT structure constants are solved by Ponsonn and Teschner. If you're not familiar, it's fine. Don't worry, it's just some Liouville parameterization. The important thing is that I told you the bulk is coming from the BCFT OPE coefficients. And in this case, the BCFT OPE coefficients actually take a very special form. It was not appreciated before because people choose a different normalization, but we just found that if you normalize it by dividing, for experts, you divide all the by the bulk end boundary reflection coefficients, and then you can see that the BCFT OPE coefficients exactly look like this. So there are 3 constants here, which I'll just explain in a minute, and something called UQSL2R quantum 6J symbol. Interestingly, this is exactly the same as the Virasoro fusion kernel. That's actually discussed a lot these days. There's a parameter B here. I want to tell you the B here is related to the central charge. The large C limit corresponds to small b limit. And the interesting thing is that this prefactor, what is it? It actually is nothing but the carbon density of state, which is the Planger measure of this quantum group, actually. And to close the holes, we have to do a weighted sum. So what do we do in this case? So this is one actual example. In Liouville, there is no vacuum state in the physical spectrum.
So why does it work to close the holes?
Yes, it's because it's really let me tell you how to say this. Because really, when you cut stuff open, it's a block. It's not the character. So in the block, you can see, for example, when you do the weighted sum, you plug in the formulas. You can see on the dual graph, it looks like this. You do the weighted sum, you will see a diagram that looks like this, where this is a very tiny block. Using the property of a compound block, you can see it's a universal divergent factor. So the block actually can be shrunk to 0. Does that make sense?
Not exactly. I thought the small hole would give you some local operator. And you were trying to make it the identity operator.
Let me put it this way. Identity operator doesn't appear in the spectrum, but when you multiply factors using the crossing move, you can see that identity will appear. That's the you want. Yeah. Does that make sense?
I think so, maybe, yeah.
Yeah, you can show like explicitly. We check this.
I believe you. I'm just trying to understand how it works. Yeah.
It's or let me put it this way. The vacuum state is not in the physical spectrum, but you can imagine. Let me see how to say this. It's like when you have the characters in the dual channel, you only keep heavy states, but in the other channel, you multiply them, right? You get a vacuum, something like that. Yeah. So yeah, and what is this? Let's just so yeah, when you do this weighted sum, you can indeed close the hole. So let's actually to see more, a little bit more about it, because this is quite interesting. Let's look at it carefully. So first of all, this construction does work. This overlap actually is convergent. One caveat I want to say is that the Ryu construction, actually, if you directly apply it to these 6J symbols and compute closed manifold partition functions, it is divergent. It's not convergent. It's already observed in the original Virasoro TQFT paper. But in this case, we take the overlap of an open quantum state with another quantum state. And especially the omega state has scales in them. So when you combine them together, actually it is convergent. Because you can use, this guy has scales, so you can imagine include counter terms, which actually is the universal divergence there. So actually it does give you a finite answer instead of the closed manifold partition functions. So that's one thing I want to mention. Secondly, this was the case for the rational CFT. For irrational ones, you change everything into integrals. The measure here was what I just told you before. And previously, I told you these OB coefficients in the rational CFT case is the Ryu TQFT. And in this case, it's also something that was discovered recently. It is the path integral in a tetrahedron for the two copies of the Virasoro TQFT. You can show this explicitly. This is giving you exactly that. So the role played by the Ryu TQFT in rational case now gets replaced by Virasoro TQFT square, which was the proposed gravity, non-perturbative gravity path integral. And the other stuff is still here. So the picture here, let me just emphasize, you triangulate your boundary manifold, a lot of triangles. You should librate it in a bulk, they meet at some points. And that was the 3D theory you construct. So these are all algebraic. So where is geometry here? The geometry really the easiest way is to see it is by looking at the large C limit. So let's first focus on a single building block, which is this 6J symbol. The 6J symbol has 6 labels in them. I want to take the large C limit, so I slightly reparameterize this a little bit. It was very popular in Liouville literature, just to see the large C limit of Liouville theory. You see that when you do this, you do a large C limit of it. This result is nothing but the following thing. So it's exponential of 2 terms. First term is the volume of a hyperbolic tetrahedron where each of the lengths is given by this rescaled Liouville momentum. There's another term here, which is the sum over the dihedral angle multiplying the lengths. So what are they actually? So first of all, let me just mention one thing. From this, you can see that the emergent meaning of this guy is geometrical, especially the notion of geodesic length in hyperbolic space emerges from the primary labels of Liouville theory. That's the first thing. So Liouville momentum becomes geodesic length. And secondly, the first term is nothing. The volume is the Armstrong action of Einstein-Hilbert action. The second term here is also important because now, usually, if you're familiar with the volume conjecture, people write it in terms of dihedral angles. Here, I'm writing in terms of the geodesic length. And dihedral angle and geodesic length, they are kind of conjugate to each other. So when I look at the geodesic length, there is this Legendre transform H term. In gravity, it also has a natural interpretation because this type of term is the so-called Hayward-Corner term. They are there if you have multiple surfaces glued along some edge. To make sure the variation problem is well defined, you have to include this term. And you see explicitly this actually is here. So each of the building block we know is actually giving you some contribution of a hyperbolic tetrahedron. It's even true in quantum level, shown by Virasoro TQFT. But really, this was for each of them. Finally, we sum over the spectrum. We integrate over all the p's. And the interpretation is exactly, so we triangulate our bulk manifold. We sum over all the quantum geometries associated to different geodesic lengths. That was exactly the idea behind the Ponzano-Regis theory. Let me just emphasize this again. So we see that from this analysis, the BCFT primary labels and boundary condition labels, in this case, they share the same label, become the geodesic length in the bulk. And when we do the integration over spectrum, we sum over quantum geometries in the bulk. Now, really, what are we doing actually in the SymTFT picture? It is just saying nothing but Liouville theory is the diagonal gauging of two copies of Virasoro TQFT. So what does that mean? Previously, I told you can realize the theory with two boundaries. One is topological, one is physical. So there is this famous story in Chen-Simon theory and WZW model. If you want to realize a non-chiral WZW model, you put one chiral copy of Chen-Simon theory, you impose chiral boundary condition here, anti-chiral boundary condition here. In the middle, you impose some gluing boundary condition. For diagonal theories, it's just transparent. Then you fold the theory. When you fold the theory, one copy becomes two copy, and this interface now become a boundary. This boundary is nothing but saying the two halves actually are paired together diagonally. So this is exactly realizing that. And I want to emphasize one more thing, which is this is only for Liouville theory. You might think it's very special, but really, generic theories, if they share the same Virasoro defect lines, they share the same bulk theory, they share the same TFT and same RG construction, because I told you all the difference for theories sharing the same symmetry is encoded in this the yellow blob. So the RG we introduced in real space actually only depend on this shaded region, which only depend on this bulk theory. So different theories, they actually correspond to, yeah, the only difference is this topological boundary condition. And otherwise they are all the same. And I think it's very generic actually. Although we don't have another example where you can solve and explicitly see this.
Right, if
So
they have the same, they're only all the same if they have the same set of primaries of Virasoro lines, right?
yeah.
So you're talking about two isospectral theories, is that what you're?
Oh, not really. Let me see how to say this. You can condense some of them, right? So I think it was related to a comment previously. Maybe all irrational CFTs, the bulk theory is the Virasoro TQFT.
Yeah, but do you understand, I mean, do you understand that more?
I don't. Yeah, I don't. Yeah, I do want to talk with you about it actually.
Okay, sure.
Yeah.
So the SymTFT machinery like requires the symmetry to be finite, and now you're working over some continuous.
I think it's not required. It is just the examples we have are all rational.
And you expect that like the things will port over even when it's not finite.
You see, in this case, the Virasoro TQFT, if you think Virasoro TQFT is well defined, then this is the Virasoro TQFT. I totally agree. It's not well understood how to deal with general irrational theories. And I personally believe it might not be a TQFT, most likely, actually.
You say more?
When you have infinitely many defect lines, the bulk theory doesn't have to be a TQFT, right? So let me just, I don't have much time, so let me just say this really quick. So in general, solving an irrational CFT is very hard. But holographic CFTs are kind of chaotic with a very universal dense spectrum. So it was proposed by these people here that you might just replace the OBE coefficients by their ensemble average or really statistical average. And people check that it actually gives you answers for multiple copies of space-time boundaries. But really, when we triangulate the manifold, they can have self-correlation with their single copy. And we are having a paper coming up very soon explaining actually what's the theory you get when you combine this technique with the ensemble average. It does also get a lot of the gravity features. So let me just mention now the wave functions. These are all, let me just remind you one more thing. These are all for partition functions. But really the original proposal was to use tensor network to understand wave functions, especially the RT formula, and let's see how it works. So the idea is really that we consider special quantum states in ADS-CFT. And actually, those are the quantum states that we most of the time consider. Those are the states actually coming from states prepared by Euclidean path integrals in CFT. For example, if I want to study the vacuum state in 2D CFT, it's living on a circle, you can do this by preparing it, doing the disk partition function, and you get a state on this red circle. That was the way we get the state in CFT. And because it's also now gotten from a path integral, you can play the game now. The only difference is now, instead of a closed manifold, now I have to add boundaries. So just show you an example. What is about? So there are two slices here. Let me just explain it before I forget. The top surface is where you do the CFT path integral, and the bottom surface, you can think of it as the Cauchy slice. Actually, you can make it precise. So, for example, the vacuum state is living on a circle. I triangulate it into a lot of lines here, where you also include these tiny corners in post-boundary conditions. You can triangulate it arbitrarily as you want. This is one triangulation. You can also do another one, use the BCFT crossing, triangulate it like this. This will be the important step that's used to derive the RT formula. But before that, let me just mention one more thing. Why actually the mechanism behind the derivation is really, in many of the situations, yeah, I'm trying to make sense of the previous diagram on this corner. The CFT path integral, which is at tau equals to minus infinity, actually has one-to-one correspondence with the tau equal to 0 bulk slice because of this hyperbolic slicing, actually. So if you have this, for example, the vacuum state or the black hole states, they all take this form. Using hyperbolic slicing, the CFT boundary will live at tau equals to minus infinity and plus infinity. And the Cauchy slice will live at tau equal to 0. You can see they are in the same conformal class, the geometry. So geometry is actually on the t equal to 0 slice. A lot of them can be directly read off from the CFT path integral. So let me just make a quick advertisement because I mentioned it because it's related to the follow-up works that I'm going to mention. Actually, a lot of the quantum states, we just put out a paper last week. You can prove the RP formula directly, just use 2D CFT data for these so-called multi-boundary black hole states. Using some ensemble average techniques, you can show that even including the homology constraint, all the RT phases actually come from ensemble averaging and this fact that these two surfaces have this correspondence. So now let's go back to vacuum. We can also apply this technique to the vacuum state. So now, combined with the tensor network, we can actually derive and even upgrade some conjectural relations relating the tensor network to gravity. Let me show you one example, which is for single interval. There was the so-called very famous Happy code. The idea behind this derivation is that the tensors people propose have these perfect tensor relations such that when you compute the RT surface, you can push it in until you hit the RT surface. And from the stuff I just told you, I can show you actually you can derive this relation, generalize it even from CFT path integral. The idea is, suppose I have a CFT ground state, look like this. I want to consider entanglement entropy where the A bar include these two lines. So now in the reduced density matrix, I have to contract, I have set this kind of configuration where these lines are identified and summed over. But in BCFT, you can see this is nothing but the gluing. And if I impose the shrinkable boundary condition, this is nothing but a strip. So it actually turns this Bryan-Ket contraction into a BCFT propagator. And this exactly gives you the correct modular Hamiltonian for entanglement entropy and entanglement entropy for single intervals in CFT. This is like the Happy code diagram if you know what it is. If not, then that's fine. It's written in our paper. And this is for single interval. And I want to tell you that a paper will come up soon is that really the difficulty was using perfect tensor. It's not clear how to derive the multi-interval entanglement entropy for vacuum states in CFT. But the claim is that now using this technique together with the one I just told you, this one, you can derive the multi-interval RT formula actually using tensor networks and this ensemble averaging. Then it will come up soon. So finally, let me go back to the SimTFT picture because I think it's a really wonderful idea. So this is the picture. Let me just explain a little bit more. So what is the bulk doing actually? The bulk theory in the SimTFT picture is a gauge theory of CFT's generalized global symmetries. So what is CFT's generalized global symmetries in 2D? They are captured, for example, by the Verlinde lines, the topological defect lines. And how to go back? So how do we choose this this topological boundary condition? So the idea is really that it's encoded in the spectrum of 2D CFT. Okay, I'll skip the math here, but really they are encoded by the set of boundary conditions you need to sum actually. It's not obvious, you have to do some math. It was shown by Fuchs, Ranko, and Schwiegart. And those actually uniquely give you a 3D topological boundary condition and a unique 3D quantum state such that it reproduces the 2D CFT. And more importantly, it is telling, so you can think of it in the following way. This topological boundary condition is actually a way of specifying these Zij's here, if you do the 2D CFT path integral. And interestingly, the modular invariance in CFT in general is not coming from summing over all the modular images, because usually we think, usually a sum is you have some characters, you sum over its modular images, it's modular invariant, but that's not generically how a 2D CFT works to reproduce how a 2D CFT works. Instead, it's coming from a very careful choice of spectrum from the anyons in the bulk. And this is actually exactly captured by this topological boundary. The topological boundary, you can think of it as a gauging of higher form symmetries in the bulk, or in traditional language, it is just inserting a mesh of Wilson lines such that the 3D theory will terminate here. On the other side, the anyons are all condensed, or you get an empty theory, such that the theory is really a sandwich instead of intrinsically 3D stuff. So I have a question here. Really, is this the most general mechanism for the non-perturbative ADS-CFT correspondence? If this is, it has a lot of good things. First of all, it realized this idea that the CFT partition function is a quantum gravity radial with wave function. You just need to find the topological gapped boundary and then do the evolution. You get a quantum state. That is this state. You find a boundary condition realizing the physical boundary condition. So it's naturally a 3D particle with two boundaries are rewritten as a 2D stuff. Usually we think there is not another boundary, but deep in the UV, everything can happen. And usually in the huge convention, that was related to the previous question. Usually when we think of SymTFT, the idea is really a theory can have a lot of SymTFT representations. So usually we use a subset of the symmetry to build up of the bulk theory. But it seems that the general lesson, especially from the 2D CFT perspective, is very natural. So you just use the maximum amount of symmetries to build up a bulk. Then when you do that, all the kinematical data will be at this physical boundary. On the other hand, all the dynamics are in this quiche region. And this seems to be exactly the property of feature of ADS-CFT. Because the physical boundary here is just the dirichlet boundary condition we usually impose in gravity. And in 2D CFT, they become the conformal. The dynamics in 2D CFT are completely captured by the OPE coefficients, in this case by the quiche. And one comment here is that if you have infinitely many lines, it's not necessarily giving you a topological quantum field theory, although I don't have other examples. So if this really is the mechanism for the ADS-CFT correspondence, it automatically solves the factorization puzzle. Because the factorization puzzle says that if I have two independent CFTs, the ADS-CFT dictionary conventionally says that you try to find all the bulk geometries, filling in these geometries. So there are these disconnected ones. The shaded one means that it's filling in. There are also these connected ones, the wormhole contributions. So on the left-hand side, it factorizes into two contributions, right-hand side doesn't. So the space-time wormholes seem to violate the factorization of the original CFT calculation. But if the mechanism I told you is the correct bulk mechanism, then from symmetries, you know why it's factorized. Because in order to do this using a bulk computation, I need to first connect them using a 3D bulk. Then I insert two branes, the two topological branes, encoding the spectrum of the theory to make sure it's exactly equivalent to the original theory. And these branes are special in the sense that I just explained. It gauges all the high form symmetries in the bulk such that the region in the middle is empty. In condensed matter terms, it's called anion condensation, such that this becomes empty. As it is empty, it's clear it is factorized. So really, I personally believe this is the correct picture, and there must be a way to actually relate this back to that. Maybe this is a low-energy approximation, or it's also possible that maybe if you do the sum, especially in 3D, maybe it's actually equivalent. There are some observables are actually shown in this tensor model by these people. But in general, I think it's very interesting to see how this reproduces this, or if they are really equivalent. And from this perspective, I want to say one thing, which is it seems that if this is the picture, at least in one of the frames or pictures, we do not sum over all the geometries. Instead, we specify the physics by a topological boundary condition. So let me just conclude. So I told you today that there is a way to exactly triangulate a 2D CFT, which construct explicit holographic tensor networks using CFT data. In the bulk, in my case, it's Virasoro TQFT or rational, the Turaviro theory, they are TQFT, but it might be, actually in general, it's not. And we believe maximal set of generalized symmetries will constrain the dynamics so sufficiently that you can reconstruct the bulk completely and the physical boundary will become kinematical. This seems to share at least the same feature as ADS-CFT correspondence. And if this is the case, the exact correspondence might not require to sum over all the geometries. It's specified by measure. And I don't have to explain three more things to you. First of all, there's another story for the so-called ADS BCFT correspondence where we really include the brain. Instead of shrinking it, I keep it finite. There is a way to do that in this tensor network framework. There is a very similar story in 2D gravity. Yeah, I personally believe like JT gravity, double scale SYK, the bulk theory are all the same TFT of the boundary theory. And finally, from this perspective, you can actually understand quantum chaos because in 2D CFT, it's kind of natural. The bulk theory, exchanging boundary operators is just like braiding Wilson lines on the boundary. So it does capture the quantum chaos from a symmetry perspective. Okay, with that, I'll leave this slide here and end here. Thank you.
Could you elaborate on the JT gravity point?
Yeah, there is some divergences that we're still not sure. So it actually was already. So let me first forget about summing over geometries that I currently don't know how to include it here. But if you study the Schwarzian theory, then you can use in the bulk theory you use a Q-deformed Yang-Mills theory with zero coupling. That is some people call it Q-deformed BF theory.
Mm-hmm.
Then there is also a discretization formalism of it, like by Witten and McDowell. And there is a boundary condition realizing that theory where you see it is indeed gauging the symmetry of the boundary, like Schwarzian theory. And where, yeah, there's an interesting thing actually. In the double scale SYK, people have already found that it seems that the boundary theory has UQ SU1, 1 symmetry. But I think from this perspective, it might actually explain it quite naturally from the SimTFT perspective. And yeah, we are working on
it. You mentioned that you don't think it's a TQFT. So is there some specific manifold on which you can compute the path integral and show that there's a dependence on perhaps the metric or something?
Yeah, I think it will be most likely.
Probably depends on how you define the words TQFT.
Yeah. It also, the weakest violation is it can depend on volume, right? You will not call it TQFT, but still it's invariant under volume preserving diff.
Yeah.
Yeah. I don't have an example, like it's just, yeah, I would love to have one.
In the previous slide, it's that the emergence of the Einstein-Hilbert action is from some volume.
Yeah.
Volume of the box space.
It's actually exactly a very mysterious thing in math that's related to the so-called volume conjecture. The 6J symbol, when you take the large C limit, the volume of hyperbolic metric emerges automatically.
So it's not volume. I think that the volume is just the integration of square root G without the Riemann, the scalar curvature.
Oh, on shell they're the same. Like
I see.
Yes. Okay. That's why it's large C limit.
There are no more questions. Thank you. Going again.